Hey, hi folks. Today we'll be discussing about how can we create a key value data store. So, if we take an example of key value databases, we can take as a Cassandra or Redis. Now, Cassandra mostly used as a database, and Redis mostly gets used as a caching system. Now, how do we create one? So there are many examples of key value databases or key value data store which are in memory. You can take any programming language. In Java we have a Hashmap, and in Python there's a dictionary. So this is in memory. Now what if you want to persist it? So the simplest form of persistent data type I can think of is a file. So we can create a file, and since it's a database, mostly we want to support two operations. One is to set key and value, that for this given key, set or store the value. And the second operation would be get key, which says give me the value of this key if this exists, otherwise give me an error or error message. Now how do we use the file to perform these two operations? So in a simple file, what we can do is we can write whenever there is a set operation, set key value, we'll simply go into file and we'll write this key and value in a new line. Now whenever a new record, the next request comes, we'll go and append in the end of the file. So we are not doing any update operation, we are not doing any delete operation, we are simply keep on appending to the same file. If we want to rewrite key 1 with the value 3, then again I'll just go in the end and I'll add an entry with key 1 and value 3. Now since we are not doing any updation and deletion, it's pretty easy. It's a thread safe implementation. Now how do I read it? So to read it, I can scan through this file. For example, if I'm reading file from the beginning for the key 1, I'll first see, okay, the key 1 is the value 1, but I cannot return it because it may not be the latest value. So I need to scan through the entire file, right? The other optimization I can do is, rather than starting from the beginning of the file, I can start from the end of the file. And now whenever I get a value corresponding this key, I can return that, because that would be my most recent write. If I do not find anything, that means this key doesn't exist. Now how do I delete records? So since we are not updating or deleting any records in key value in this file, for delete operation we'll also do an entry in this file. We'll just create a entry with saying that key 1 and the value, I'll say it's a tombstone or deleted. That means whenever I come across this entry, I can be certain that this key has been deleted. Now let's find out how much time it takes, how efficient a database is. So if we talk about write operations, so write operation are simply O of 1. That means it's a constant time complexity I'm considering, right? There is no complex procedure I need to make. I just simply need to append at the end of the file. So it will be O of 1. But what about my read operations? So read are going to be pretty slow. I am going to start from the end of the file, and in worst case I have to traverse the entire file. So that means the number of records are present in my file, exact that much operations I may need to do in the worst case. Now this is not just O of n, like if there are n unique key value pairs, it's not O of n, because there could be multiple entries, duplicate entries. We may have done update of the same key multiple times, right? So how do we optimize this? So one of the key concept optimizing reads in a database, in a relational database, what we usually do is we create an index. Now index is a data a simple data structure will give us a good speed of reads. How can we do that? I can create a in-memory key value data store. Like I can create a hash map or a dictionary, and in this dictionary what I'll keep is key and the value would be the location in the file. So for example, if I see the key one is now present at line number 53, I'll just keep that. If key 2 is at line number 2, I'll keep that in Hashmap. Now if you want to write into this database, I can simply go and do this operation in constant time complexity, and if you want to read it, I can do the same in the constant time complexity. How so? I'll simply check my hash map where this key is located in the file, and I can simply go to that file, read this record and return it, right? Now both the operations are in the constant time, but there's one problem. Since our key value database is based on a file and we are just appending it, there could be a time when we can run out of space, because we are updating or appending to the same file again and again. Now for example, we have created a database that how many times this post on Instagram has been liked. So whenever a like somebody likes this, we have to increase that number and we have to make an append entry, right? We are not updating it. So pretty soon, if there are 1 million likes, we have to make 1 million entries. So that's not a very optimal solution. So how do we achieve that is, since we are also sure that these files are only we only want the latest data. So for that, what we can do is we can create multiple files. So whenever there is a size limit reach in our file, I'll just start a new file, and now what I'll do, I'll be running a compaction algorithm. So I'll be merging the records and then I'll creating new files. So for example, if I have two files, A and B, and A has record from 0 timestamp to 0 plus 10 minutes, right? So initially 10 minutes writes in this file, and the remaining 10 minutes write operation are in the file number 2, file B. Now I know that which records are latest. So if the entry is present in A and B both, I'll consider that B's entry is correct and if it doesn't exist in B, then I can take that A's entry correct. So I'll be, for the keys which are unique in A and B, I'll take both, and if there is a overlapping entries in A and B, I'll consider whichever is latest. Even if there are multiple entries in B itself for the same key, I'll take the latest. So that way, after some time, I can keep running this compaction algorithm, and this way I will no longer be running out of space. Now this compaction is not very efficient though, and but yeah, so this is not very efficient. And in our read also, we took an assumption that we'll create a hash map, in-memory hash map, but the complexity with in-memory hash map is we it's in memory. So now if you have to restart your system, or your database crashes, your entire hash map gets crashed. So now if your hash map crash, what you'll do, you have to, whenever your system restart, you have to rebuild your hash map, and that may take a lot of time. You're rebuilding your indexes, right? So uh, the other solution could be, for example, suppose if there is a way to keep these key value uh, sorted based on the key. That means I can even perform the range queries, and if I want to write something, I should be still able to write fast enough. How do I do that? Suppose you have a binary tree, or a height balance binary tree, that could be a red black tree. Now you want to add a new record in this binary tree. How do you do? You go to the root, you find out either I need to go to left or right, and you'll be keep performing that operation until you find the appropriate location, and you will simply create a new node and add it there, right? So if there are n number of nodes in the tree, the you'll be traversing of log n, that means the height of binary tree. And since this tree is height balance, that means it will be always guaranteed log of n, right? So now if somehow I can have this height balance binary tree kind of structure, I can perform range queries, and at the same time my writes will be faster, right? And since I can run a range query, that means I don't have to build my index as a dense index. I can create a sparse index. So what is a sparse index? Rather than creating each key and that location, I will store a very less number of keys and value line or the location of that. So for example, every 10th record I can keep an entry in my hash map that now this exists at this place. So this helps because now I'm not really dependent on the size of my database, right? So now if we are able to create this height balance binary tree, uh, we can also push that into a disk, right? Now the records in this will be again sorted based on the key. So I can run a range query, I can build a sparse index. So when I keep this in hard disk, this is called as a table or sorted string table, right? And when I was keeping it in memory, it was called memtable, that means in memory table. Now when so whenever I'll get a write operation, I'll not directly write into SS table, I'll simply add an entry into mem table. That will be pretty easy of log an operation since it's a height balance binary tree. And once this as mem table reach to a particular size, I can uh, dump into hard disk or my persistent memory, and it will be converted as a SS table. Now I'll be having bunch of SS table and one mem table, and I can even run the merge and compaction operation on these SS table pretty easy because my SS tables are sorted based on the key value pair, right? Now you must be aware about an algorithm which says that there are n arrays and all are sorted. Now you want to merge them. How do you do? You can just keep n pointers, and at every moment you just see what should be the next value coming up, right? There are further optimization to it. I will not go into detail like how to use heap and all, but it will be the same problem. Now the compaction is easy, and write operations are fast. How do you read it? You can simply go to first you'll check into the memtable if this key exists in the memtable. Now without index also it will be pretty easy, but for example, you'll search in this binary tree. If you don't find it there, you go to the next SS table. If you don't find it there, you go to the next. Now this is again, it could be a problematic situation where you may have to go to all the SS table. So to optimize this, there are concepts like Bloom filters. Bloom filters basically is a probabilistic data structure which tells that something may exist or it doesn't exist at all, and that's a guarantee. So uh, that's an optimization. We'll talk about that in future video. So, and this whole scheme called LSM tree, actually that there are a bunch of SS tables, mem tables. Now one key problem, that what if you have done a write operation that is in your mem table and now your database crashes? How do you handle that? Because you just kept it in memory, and if your database crash, your hash map is gone or your mem table is gone. Now you can't find that entry. So the same concept which we discussed in the beginning, now we'll take it name. It's a write ahead logging. Then that will create a log file, and log files are append only. So we'll keep a log file where we'll be not the updating, we'll be adding this entry whenever we'll be doing a write operation. So at any moment, if our database restart, we can replay all the records from this log file and we can reconstruct our mem table as it is. So whenever we dump this mem table into database and create the SS table out of it, we'll also delete this log file and create the new log file. So this concept is exact same concept is used in database like Cassandra, and there are further details to it we'll discuss in the next videos. Thank you.